All right, today we're tackling what's basically the capstone of intermediate algebra, sketching polynomials completely by hand. This is where all those skills you've been working on, like factoring and finding zeros, finally click together into one really powerful process.
So let's just dive right in. Take a look at this function. Without a calculator, how would you even begin to visualize what this thing looks like? I know, it seems pretty intimidating at first glance. But believe me, by the end of this, you'll have a clear plan to sketch this thing, and pretty much any other polynomial you come across. And here it is. This is our blueprint. This 5-step checklist is the secret weapon. It takes all the guesswork out of graphing and turns it into a logical, almost foolproof system. So let's break down each step.
We're going to start with the first 3 steps. I like to think of this as building the skeleton of the graph. It's the absolute basic framework. It tells us where the graph is coming from, where it's going, and all the spots it hits the main horizontal axis.
First up is end behavior. This is the big picture, the 30,000-foot view. Before we get into any of the little twists and turns in the middle, we just need to know where the graph's arms are pointing. Are they both going up, both down, or are they heading off in opposite directions?
And what's awesome is that this whole thing boils down to just 4 possibilities. It all depends on 2 simple things. The polynomial's degree, is it even or odd? And its leading coefficient, is it positive or negative? An even degree, like x squared, makes a U shape, so both arms go the same way. An odd degree, like x cubed, means they go in opposite directions. It's that simple.
Now, let's move on to the next parts of our skeleton. Finding the zeros is pretty straightforward. It's just finding the x-intercepts, where the graph hits the x-axis. But the real secret sauce here is multiplicity. This tells us how the graph behaves at each of those points. And this is the key difference right here. If a zero has an odd multiplicity, like 1 or 3, the graph just slices right through the x-axis. But if it has an even multiplicity, like 2 or 4, the graph comes down, just kisses the axis, and then bounces right back off. This whole cross versus bounce idea is the secret to getting the shape right.
Okay, so our skeleton is built. Now it's time to add a little bit of flesh to those bones. These last 2 steps are all about adding the details and the precision that will really bring our sketch to life.
Step 4 is all about finding the y-intercept. The source material calls this the anchor point, and that is the perfect way to describe it. By plugging in 0 for x, we find that one single point where our graph crosses the vertical axis. It totally locks our curve into place.
And finally, we just fill in the gaps. We'll pick a couple of test points, usually in between the zeros we already found, just to see if the graph is above or below the axis in those areas. It helps confirm the shape of our hills and valleys. After that, all that's left is to connect everything with a nice, smooth curve.
All right, enough theory. Let's get our hands dirty and actually put this blueprint to work. We're going to take this function right from the source and sketch it from start to finish using all 5 steps. Okay, here we go. First, end behavior. For that, we need the degree and the leading coefficient. Now, to find the degree when a polynomial is all factored out like this, you just have to add up the exponents on each factor. So we've got a power of 2, a power of 1, and another power of 1. You add those up, 2 plus 1 plus 1, and you get a degree of 4. So a degree of 4 is an even number. And you see that negative sign sitting out front? That means our leading coefficient is negative. If we check our mental cheat sheet, an even degree and a negative coefficient means both ends point down. So our graph is going to start from the bottom left, do its thing in the middle, and end up heading down to the bottom right.
Next up, let's get those zeros and their multiplicities. Since this function is already factored for us, which is awesome by the way, that's half the work. All we have to do is look at each piece and figure out what value of x would make it 0. Okay, so we get zeros at x equals -1, +2, and +4. Now for the important part, cross or bounce. Well, the 0 at -1 comes from that squared factor. Since 2 is an even multiplicity, it's going to be a bounce. The other 2 zeros have a multiplicity of 1. And since 1 is odd, the graph is going to cross right through the axis at both x equals 2 and x equals 4.
Time for our anchor point. To find the y-intercept, all we have to do is plug in 0 for every single x in the function and just see what number pops out.
So f of 0 is negative times 1 squared times -2 times -4. You multiply all that out, and it simplifies to -8. So we know for a fact the graph has to pass through the point 0, -8.
This is what anchors our curve between those two zeros at -1 and 2. We are so close. We've got almost everything we need. We know the graph crosses the axis at x equals 2 and again at x equals 4. But what happens in between? Does it go up or down? A really quick test point will tell us exactly what to do. Let's just pick a number right in between them, like x equals 3. When we plug in 3, we get positive 16. That means the graph is definitely above the axis in that section. Okay, now we can draw the whole thing. We start from the bottom left, come up to the x-axis at -1, and bounce. Then the curve dips down through our anchor point at 0, -8, swings back up to cross the axis at 2. It's going to hit a peak somewhere around our test point, and then it crosses back down at x equals 4, and just keeps on falling forever. And there it is. Now that you've got the process down, let's talk for a second about why this is such a critical skill. I mean, this isn't just about passing a test. It's really about understanding the shape of things and avoiding a few really common mistakes. This right here is the #1 mistake I see students make. They connect their points with sharp, jagged corners. You have to remember, polynomials are always smooth, flowing curves. Think roller coaster, not lightning bolt. If your graph has pointy bits, you've got to round out those turns.
And let's just come back to this quote from the source material, because it is so important. Forgetting that y-intercept is a huge pitfall. Without that anchor point, you might draw the curve between your zeros way too high or way too low, and that completely changes the look of the graph.
And if you think this is just some abstract math class thing, think again. This has some amazing real-world connections. Engineers who design roller coasters, they are essentially just sketching polynomials. The zeros are where the track is at ground level, the turning points are those awesome hills and valleys, and the end behavior is literally the start and finish of the ride.
So now you have the blueprint. The next time you see a curve out in the world, and they are everywhere, the path of a thrown football, a company's profit chart, the curve of a bridge, you now have the blueprint to start analyzing and really understanding the math that's shaping it. So what else could you apply this to?